Although embeddings are a better solution than one-hot encodings, what embeddings lack is enough context and are typically applied in a context-free manner. That is, the vector for a word is unchanged irrespective of the context. Consider these two sentences: open a bank account and on the riverbank. Note that while we use the context to learn embeddings of a word during the training process of the embeddings, we do not consider the context while using it in the downstream models. For example, assume that you have a very simple bag of words model where you just average the representations of the word in a sentence to come up with a sentence representation. In both the sentence representations for the bank account and the riverbank, you would use the same embedding for the word vector bank. Now, this is problematic because clearly the word bank has two different senses in two different contexts. What is desirable is to have that you need different vectors for different contexts. Now, how do we do that? One way to do this is to build models which improve the contextual understanding of a sentence. In building these models which understand context well, the objectives which are typically used to train these models are based on classical language modeling objectives. In a classical language model, the objective is, given a sequence, we need to find or predict the next word in this sequence. Now that we want to build parameterized models which understand context, you could use the classical language modeling objective and train models that are parameterized to keep on predicting the next word. In doing so, it uses the past context to predict the occurrence or appearance of the next word. In this example, we train the parameterized model by masking the last word of the sequence on the river. And then we try to update the parameters of the parameterized model such that most of the probability mass is accumulated on the word bank instead of other words which are unlikely or improbable. These models that use the language modeling objectives are called language models. Language models can take input sequence of text and can be trained to output input representations of either the next word or a sequence of words or given a vector for the input representation. Because it can be trained by this simple language modeling objective to output a word, a sequence, and a vector, these language models can be used in a variety of language tasks. A note about the implementation of these language models. While most of the classical language models were based on count of words or co-occurrences of words, all the modern language models are based on deep over-parameterized neural models. Some examples of these neural network models are recurrent neural networks, transformer architectures, for example, BERT, RoBERTa, and AccelNet. We look at one of these architectures, which is called the bidirectional encoder representations from transformers, or in short, BERT. BERT has been a very popular deep learning architecture for natural language processing, which was developed by Google in 2018. One of the ideas to train the BERT model is to extend the classical language modeling objective by using a slightly modified objective, which is called the masked language modeling objective. In the masked language modeling objective, instead of predicting the last word, you try to predict arbitrary masked words in the middle of the sentence. The advantage of using the masked language modeling objective is that you're using both the previous and the subsequent context to predict the missing word. This allows the parameterized model to understand the context of the sentence better than trying to predict the next word or the previous history of the sentence. Apart from the masked language modeling objective, BERT also has another objective. In this objective, BERT tries to predict from a pair of sentences if the next pair of sentence or the next sentence is following the original sentence or is a random sentence from the text. This objective is called the next sentence prediction objective. What is interesting to note here is that BERT model marked the beginning of extremely large novo-parameterized models for NLP. Specifically, the original English language BERT has these two models, the BERT base model, which has over 110 million parameters with 12 encoders and 12 bidirectional layers, and the BERT large model, which has 24 encoders and 16 bidirectional attention heads. Now, both these models are pre-trained from massive amounts of text data. From the book corpus, which around 800 million words, and English Wikipedia with over 2,500 million words. The BERT model consequently resulted in huge improvements in many NLP benchmarks and many NLP tasks. The key insight for the success of the BERT model was the transformer block which was used in the BERT architecture. Transformers used in the BERT model heavily rely on the self-attention mechanism. For the scope of the lecture, we omit discussing the self-attention mechanism, but it suffices to say that the self-attention mechanism focuses on all pairs similarity of the words which are present in the input in computing the contextual representation of a sentence. This presence of self-attention mechanism results in a better contextual understanding of the words and hence the contextual understanding of the input. And therefore you see large improvements in a lot of NLP tasks.